In this video we introduce Monte Carlo simulation. Think of Monte Carlo simulation as scenario simulation with a twist. It was developed during World War II for the Manhattan Project, and for those of you that know your history, the Manhattan Project was the project that developed the atomic bomb that was dropped in Japan. The idea was to model nuclear fission reactions. What Monte Carlo simulation does is it uses a much richer set of inputs than scenario simulation. In scenario simulation we input specific values for the different scenarios, and then we tediously change the values and we take a look again at what's happened. In Monte Carlo simulation, instead of a number that changes, we just put in one probability distribution, and then we draw a value from that probability distribution, and that value that is drawn serves then as the input for one iteration of a particular model. And for the output, we accumulate all of these, the results of all of these random draws in our spreadsheet, and we end up with a probability distribution of the outcome. So instead of a table of 9 by 9, for example, for EBITDA, we're going to end up with a complete probability distribution for EBITDA given the assumptions that we put in. Now we're going to flesh this out with numbers and graphs going forward, so hang in there. Theoretically, we could do this mathematically. We could define all the different distributions for our input variables, and then we could crunch a bunch of numbers and we could actually come up with or calculate the probability distribution for our output variable. Well, we could if we had PhDs in statistics and if we were Yoda. Monte Carlo simulation gives us a shortcut around that. What we're going to end up with is a simulated probability distribution for our output variable, and we'll see if we run enough iterations in our Monte Carlo simulation, it's going to be very, very close to the actual distribution for our output variable, and it's a whole lot less work. Not only that, you and I can do it. There is warning, of course, and that is you have to think hard about the probability distributions that you use as your input variables, because if they don't capture the risk that's in your system, you're not going to get a very usable model. It's the typical garbage in, garbage out problem. Okay, how it works in general. Well, we have inputs, and think of all those numbers that go up into the input section that you've then named. Those are the input variables. What we're going to do is define them as random variables. In other words, we're going to give each one of those input variables, or many of those input variables, a probability distribution of its own. We're going to take one draw for each of our input parameters. We're going to calculate the spreadsheet based on that draw for each of those parameters, and we're going to save the output. Then we repeat the process, and we repeat the process again, and we repeat the process again. We repeat the process thousands of times. What we get at the end is a frequency distribution of the consequences of our decisions. In other words, the frequency distribution of the output variable. It will approximate the true relative likelihoods of the different consequences, provided we've made enough iterations, and it will allow us to assign a probability for each of the possible outcomes. And that's pretty darn nifty. Okay, for EBITDA, what we're going to get is a probability distribution of EBITDA instead of a 3 by 3 table. And it's going to enable us to explicitly assess the risk of EBITDA. How bad could it get, and what's the likelihood of it getting that bad? So how does it work? Well, with our EBITDA model, we only have two inputs. We have growth and we have cost of goods sold. And let's start and assume that both growth and cost of goods sold are normally distributed. That's what the tilde n here, with a 6% mean for growth and a 3% standard deviation, and an 80% mean for cost of goods sold and a 5% standard deviation. Now, let's take a quick aside. I've alluded to this already. The number of iterations in a Monte Carlo simulation is important. It determines how close your simulated distribution is to the actual distribution given your assumptions. So the greater the number of draws or iterations, the closer your simulated distribution is going to be to the true distribution. What it means, of course, to you from a practical standpoint is that you just need to run enough iterations in your model. Typically, given the power of today's computers, you can run 10,000 iterations in the blink of an eye, really, so it's not that big of a problem. You'll use @RISC's Latin hypercube sampling method. Is pretty much the state-of-the-art of Monte Carlo simulation, and it minimizes sampling error. It's the default setting in @RISC, so you don't need to mess with it. Let's take a look and see how the number of draws affects the ultimate distribution. So this is simply the draws for the cost of goods sold for 50 draws right here, and you see this is clearly not a normal distribution. The right tail is longer and fatter, the left tail is smaller. Here's one for 500 draws, and you can see it's closer to normal, but again the right tail is heavier. In this part, the left tail over here is longer and thinner. It's still not a normal distribution. And finally we come down here, and I produced this distribution or histogram using 5,000 iterations, and now you see this thing is very nearly symmetrical, which is what the normal distribution should be. We see 4 bars here from a very thin one to a moderate one, and we see the same size 4 bars over here. We see the steps up are almost identical. So this is a true normal distribution. It took us 5,000 iterations to get here. Now the outcome of a simulation that I ran of 5,000 draws for EBITDA looks like this, and you can see it's not quite normal. Well, the product of two normally distributed variables is not necessarily normal. The sum is, but not the product. What we see is kind of a long right-hand tail. What we gain from this now is we have a mean of 212. Well, that's what we expected anyway, but notice the minimum given our assumptions is now a minus 7.5, whereas it had been with our previous worst case scenario was 155. The maximum, in other words, if we got really good draws for both the growth rate and the cost of goods sold, is almost 500. Now compare this to the 3x3 table that we had earlier. There's simply no comparison between the amount of data. We can ask all kinds of questions of our probability distribution, such as what's the likelihood of EBITDA being greater than 120? Well, in this case, it's about 95%. What's the likelihood of it being over 311? That's about 5%. Nowhere in this table can we ask and answer that question. There's another benefit that I alluded to briefly, and that is with Monte Carlo simulation, it makes combining different distributions a breeze. As I mentioned earlier, if you add normal distributions, the result that sum will be normally distributed. However, if I multiply normally distributed variables, the product is not necessarily normally distributed. And if I multiply a normally distributed variable and a uniformly distributed variable, the result will most definitely not be normally distributed, and it involves a remarkably complex calculation to find out exactly how it's distributed. Well, with Monte Carlo simulation, you simply define, say, growth as normally distributed and cost of goods sold as uniformly distributed. By uniform, we mean it can assume any value between 0.75 and 0.85. Run your Monte Carlo simulation, look at the histogram, and you can identify the distribution. @RISC even has a function that will allow you to identify the distribution and its parameters should you be so inclined. So here's EBITDA. Here's what it looks like if cost of goods sold is uniformly distributed instead of normally distributed. You can see it's no longer a normally distributed random variable. It has a very short, fat left tail and a fairly long and thin right-hand tail. Now, to give you an idea of how to compare the two, this graph also comes out of @RISC. The red line is the product of a uniformly distributed cost of goods sold and a normally distributed growth rate, and the purple line here is the result of both growth and cost of goods sold being normally distributed. So you can compare the distributions like this, and clearly they are different. Again, it would not be fun to calculate the distribution for this red line. what we're going to do next is introduce you to simulation software, and the simulation software that we're going to use is At Risk.